Hello everyone, this is Mr. Fawcett and we are back for another lesson in our AP Calculus AB journey. Today we're going to talk about limits at infinity, which may sound something like infinite limits, which we talked about the last couple of lessons, but you're going to see that these are quite different. And while infinite limits had a relationship with vertical asymptotes, we're going to be talking about limits at infinity and the relationship with horizontal asymptotes of functions. This is actually going to be a three-part video, I believe. There's quite a bit of information here, even though the notes are not that long. We are going to be going back and discussing our knowledge of horizontal asymptotes and end behavior based on what we talked about in our pre-calculus and algebra 2 classes. So there's not going to be a ton of new calculus, especially in the first video, but we do need to reinforce that knowledge we picked up in our previous courses. So let's jump right in. Up until now, we have only looked at finding limits as functions approached real numbers, specifically integers. However, we can also look at what happens as functions approach infinity. From algebra 2 and pre-calculus, you have referred to this as end behavior. And the first part of this lesson is going to be us talking about the end behavior specifically of polynomial functions. We are going to start off with a quadratic. So we have a limit expression. It says find the limit as x approaches infinity of the polynomial x squared plus 6x plus 10. So basically this is asking us what happens as we substitute larger and larger positive numbers or larger and larger x values or inputs into the above function. That's going to tell us what the limit as x approaches infinity is, because we can't just try direct substitution here, right? We can't substitute an infinity into a function. Infinity is not a number, so we're not going to get a specific output if we attempt to do that. Then you're also going to think for number 2, what happens as we substitute larger and larger negative numbers into the above function? And this would represent the limit as x approaches negative infinity. So I want you to think about those two questions. You don't have to come up with answers to the limits, but I just want you to think about what's going on as we change around those inputs. And then we'll talk about the relationship with the answers to what these limits would be. And feel free to experiment with your calculator, make a table if you want, or just think about it analytically. Okay, so hopefully you've had some time to think about these two questions. The first thing I'm going to do is sketch a graph of what a quadratic function looks like, and specifically this one where our leading term is positive. So we're going to have a quadratic that opens upwards. I know that may not be the exact, well, it certainly isn't the exact placement of this quadratic. I'm just showing you the general shape of a quadratic where the leading term is positive. So it's going to be opening upwards. Now, we need to think, okay, what's happening as we substitute larger and larger x values into the above function? A couple ways we can do this. If we have access to our graphing calculator, right, we can just graph the function and look. As the x values become more positive, our y values are approaching infinity, or they're increasing without bound. So y values approach infinity. Again, another way of writing that is increase without bound. And you can choose which way you write it. I just want you to be aware that those two phrases mean the same thing. Now, if you didn't have access to your graphing calculator, you could sit here and make a table, right? You could make a table of x values and y values and just make the x values constantly get larger and larger and larger. But it's a bit tedious, and we don't want to have to keep doing that every time we come across one of these problems. If we think back to end behavior from pre-calculus or maybe algebra 2, we should remember that we can look at the leading term of the function. So not only does the leading term of the function tell us whether the end behavior is going to be the same right? If our exponent is positive and even, then the end behavior is going to be the same for both as the x values go towards positive infinity and as the x values go towards negative infinity. If that leading, and this is the case right here, right? We have a 2, which is even, so our end behavior is going to be the same. Now, if that was an odd exponent, then the end behavior would be different. So the function would be increasing without bound, or going towards positive infinity on one end and negative infinity on the other end. So that exponent on the leading term can tell us what's going on with the end behaviors, whether they're the same, whether they're different. Now the sign of the first term, right? So this first term is positive x squared. If that first term is positive, then as we substitute in positive numbers, that sign's not going to change, right? It's going to stay positive. So without looking at the graph, as the function's x values approach positive infinity, the y values are going to approach positive infinity as well. If the function has a negative sign in front of the leading term, then we would have to think about it a little differently. And we'll do an example of that in a second. But the answer to this would be positive infinity. The y values are getting larger and larger and larger without bound as the x values get larger and larger. If we come down and look here, again, we already know that the y values are going to get larger and larger even as we substitute in larger and larger negative x values. We've already talked about that as we looked at the graph, and we talked about it based on the exponent being even or odd. So again here, the y values approach infinity. And our answer here, the limit would be negative infinity. So real quick, let's talk about if the sign of the first term was negative. So let's say I just had another function, or we'll do the limit as x approaches, we'll do negative infinity here, of negative x squared minus 5x. So we could think about what the function is going to look like. All right, this is going to be a parabola, but it's going to be opening downwards because that first term is negative. So the answer to this limit, it doesn't matter whether we were doing the limit at positive infinity or the limit at negative infinity. It's still going to be negative infinity. See if I can do it. Okay, good. My screen didn't shoot off to the side. But we don't have to graph this to do it, right? If we look at this first term, right, the sign is negative. So if I substitute in positive numbers, well, I square the positive number, it's going to be positive, but then I have to multiply it by -1, so it's always going to be negative. If I substitute in negative numbers, and that's what I really should think about because my x's are approaching negative infinity. If I substitute in negative numbers, I'm going to square them, which makes them positive, but then I'm going to multiply by -1, which is going to make them always negative. So as x approaches negative infinity, the y values are going to approach negative infinity here as well. So you can think about this analytically. You do not have to graph this to understand it, and you may not be able to graph it with your calculator at least, because you may have a question where it's on the non-calculator section. Okay, so that was our review for quadratics. Let's now just change this quickly to a cubic and talk about the same types of questions. So same questions, we're finding the limits as x approaches positive infinity and as x approaches negative infinity. Try this on your own and try it without using your graphing calculator. So think about, could you figure out what the y values are approaching? Or think about the end behavior of the function without graphing it or using your calculator to make a table. Okay, hopefully you've had some time to look at that. Let's talk about the limit as x approaches positive infinity first. So we really only have to pay attention to this term, right? Because that's the significant term. It's the one with the highest exponent. It's going to change the quickest, which means it's going to essentially define what the function is doing. So as I substitute in larger and larger x values, well, if I'm cubing a positive number, that number is always going to stay positive, right? And it's going to increase as I increase the x value. So my y values approach infinity. So the answer to this limit would be positive infinity. Now down here, let's use blue. I'm looking at the limit as x approaches negative infinity. So as we look at this first term, again, because that's a significant one, we are substituting in larger and larger negative numbers. So if I cube a negative number, I'm going to, the number is going to stay negative, right? If I cube negative 2, that's going to be negative 8. So if I keep substituting in larger and larger negative numbers, my y values are going to approach negative infinity, not positive here. Okay, and once you've thought through that, you could check your answer with a calculator. I'm just going to show you what a quick graph of this cubic function looks like, but most of you probably have an idea. Because the first term is positive, this cubic would look something like this. Again, that's just the general shape. So we can see that as we move towards larger and larger x values, the function approaches positive infinity. And as we move towards more negative x values, the function approaches negative infinity. Okay, let's move on to the next page and try to summarize our thoughts for polynomial functions. So it says, write a rule for taking limits at infinity of polynomial functions, both positive and negative infinity. Is there a way to figure out the end behavior, or what the function will approach, without substituting? So take a second, try to summarize your thoughts. Again, we kind of talked about this, how we could figure out the answers to those limits analytically, rather than having to use our calculator to sketch a graph or make a table. All right, so I put the answer that I came up with on here. I'm just going to read it as you read it along with me. So check the exponent and sign of the leading term. That is what matters. As long as the polynomial is in standard form, of course. The other terms do not play a significant role, so we do not have to worry about them. So example, down here, I just came up with another example. This is the only term we need to look at. And we need to look at the exponent, and we need to look at the sign. Those two things will tell us what the end behavior is, which will tell us what the limits at both positive and negative infinity are. So for this example, if the exponent degree is odd and the sign is negative, then the limit at infinity will be equal to negative infinity. And again, we can think through that. If I'm substituting in larger and larger positive numbers into this term right here, right? If I cube a positive number, it's going to stay positive. But then I'm multiplying it by a negative 4, which is going to always make it negative. So as my numbers increase, my x values increase towards positive infinity, my y values are going to get more and more negative. And the opposite is true if I'm looking at the limit as we go to negative infinity. If I substitute in a negative number, if I cube a negative number, that's going to be another negative number, times negative 4 is going to give me a positive. So as I substitute in more and more negative x values, my y values are going to get increasingly positive. Okay, and that's why that limit, which I underlined right here in pink, is going to be equal to infinity. So this graph would actually look something like this, okay, for this cubic. Okay, hopefully that was a good review of just polynomial end behavior. I don't think I've taught you too many new things in this video other than the relationship between end behavior and the limit expression. So the new thing is relating end behavior to another type of another form per se, where we rewrite essentially the end behavior as a limit expression rather than what we've talked about in pre-calculus and algebra 2. So when we come back for our next video, we are going to get into looking at the end behavior and limits at infinity of rational functions. They're a little bit trickier because they're not as straightforward as polynomials. You've got a quotient going on, but we will dive into them shortly. All right, this is Mr. Fawcett. Enjoy the rest of your day.